Hey everyone, welcome back to Astronomy Daily. I'm Anna.
And I'm Avery. It's Thursday, August 20th, Series 5, Episode 172.
And we're leading with a genuine milestone today. China's commercial space sector just proved it can land a rocket, not just launch one.
LandSpace sticks the landing on Zhu-Q3, first time any Chinese private company has pulled that off.
Then a planet that's somehow 23 times heavier than Earth while barely being any bigger, which really shouldn't be possible. A star doing laps around our galaxy's supermassive black hole faster and closer than anything we've ever tracked. And new James Webb data suggesting the early universe has been hiding a huge chunk of its mass from us this whole time.
Plus tonight, good excuse to actually get the telescope out and look at some craters.
Lots to get through. Let's get into it.
Okay, so China and rockets. We were just talking about this 2 episodes ago, right? The Long March failure and the fast recovery.
Right, but this is a completely different story, and honestly a bigger one long term. That was China's state space program, Long March rockets run by the state-owned main contractor. This is China's commercial sector, and specifically a company called LandSpace.
Which does what exactly?
LandSpace was founded back in 2015, one of the first wave of Chinese private launch companies. Their rocket is called Zhu-K3 or ZQ3, and it's a big one. Stainless steel construction, liquid methane propulsion, standing 76.6 meters tall. For comparison, a Falcon 9 is about 70 meters. This thing is taller than what SpaceX flies.
So already an ambitious vehicle before you even get to the landing.
Exactly, and landing is the part that matters here. Zhu-K3 flew for the first time back in December 2025. That flight actually reached orbit successfully, which is already a big deal for a new rocket, but the landing attempt on the first stage didn't work out.
So this was a do-over.
This was the do-over, and yesterday, August 19th, they nailed it. Liftoff was from the Dongfang Commercial Space Innovation Zone in northwestern China, and about 8 minutes after launch, the first stage came down on 4 landing legs, roughly 390 kilometers downrange, out in Minqueen County, Gansu Province. It came in on a single Tianque-12 engine, touched down close to dead center on the pad.
8 minutes from launch to landing? That's a very SpaceX-shaped timeline.
It's the same basic playbook, yeah. Boost, separate, flip, come back down under power. Nobody outside SpaceX had made that work on an orbital-class booster with actual repeatability until now. There have been a couple of smaller Chinese hop tests and suborbital attempts from other companies, but landing an orbital-class booster on a real orbital mission is a different tier of difficulty.
What does LandSpace actually get from one successful landing? Is the booster flying again next week?
Not next week, no. This is very much a prove the concept flight rather than a ready for daily reuse flight. But it's the step everything else depends on. LandSpace themselves are framing it as moving toward the engineering application phase of reusability. In other words, this is where you stop asking, can this work at all? And start asking, how do we make this routine?
Any hiccups? These things usually aren't perfectly clean.
The core landing itself was clean. Legs deployed, touchdown where it was supposed to. Some reporting mentioned activity in the aft section of the booster after landing, which, given this is methane-fueled hardware coming down hot, isn't unheard of even on successful landings. SpaceX has had post-landing fires on otherwise successful Falcon 9 recoveries, too. It doesn't take away from the fact that the vehicle landed intact and upright.
So, bottom line, why should our listeners care about one Chinese company landing one rocket?
Because reusability is the thing that actually changes the economics of spaceflight. It's why Falcon 9 turned SpaceX from one very good rocket company into the company that now launches more than anyone else, multiple times a week. China's had a state-level reusable rocket effort in progress for years, but this is the first time a private Chinese company has shown it can do the hardest part. LandSpace just put itself in what's genuinely a very short list of organizations on Earth that have landed an orbital-class booster.
A list that's about to get a little more competitive.
Which is good for everyone watching prices, honestly. Next up, over to exoplanets, and a planet that's breaking the rules just by existing.
Go on.
It's called GJ523b. Team led by Max Croft at the University of Wisconsin-Madison found it using NASA's TESS spacecraft, then confirmed it with follow-up observations from the WIN 3.5-meter telescope at Kitt Peak in Arizona. Here's the number that makes it interesting. This planet is 23 and a half times the mass of Earth.
Okay, so a mini Neptune, gas envelope and all.
That's exactly what you'd expect, and that's exactly what it isn't. It's only about 2.5 times Earth's width. Do that math, 23 times the mass and barely 2.5 times the size, and you get something extremely dense, and as far as they can tell, mostly rock, not a puffed up gas world at all.
Why is that a problem?
Because planet formation models are pretty clear on this. Once a rocky core gets big enough, and 23 Earth masses is well past that threshold, it should have enough gravity to grab a thick hydrogen-helium atmosphere from the disk of gas around its young star and balloon outward, the way Neptune or Uranus did. DJ523b had every opportunity to do that. It orbits its star every 17.75 days, and the whole system is only about 170 million years old, young enough that there should have still been plenty of gas around when it formed.
And instead, it just didn't bother.
Instead, it just stayed rock, all the way up to 23 Earth masses. Croft's own quote on it was, "This isn't what we expected at all," which for a planetary scientist is basically shouting.
So what's the explanation?
Honestly, right now, they don't fully have one. Maybe it formed somewhere else, closer in a gas-poor environment, and never had the chance to accrete an atmosphere. Maybe it did have one and something stripped it away early. That's the appeal of finding it. It's a genuine outlier that doesn't fit the models, which usually means there's a piece of planet formation physics we're still missing. I'll flag, this result's been submitted to the Astronomical Journal but hasn't gone through peer review yet, so consider it an exciting first look rather than a settled result.
The universe's way of telling planetary scientists they're not done yet.
It never is.
All right, this next one is genuinely one of my favorite kinds of stories. Extreme physics, extreme numbers.
You're going to like this then. There's a star, newly cataloged as S301, that's been found orbiting Sagittarius A star, the supermassive black hole at the center of our own galaxy.
We've talked about the S-stars before, right? The ones that whip around Sagittarius A star on tight orbits.
We have, and S301 just took the crown from all of them. It gets within 12 astronomical units of the black hole at closest approach. That's closer than any star ever tracked around Sagittarius A star, moving at roughly 25,000 kilometers per second. And it completes one full orbit in just 8.7 years.
8.7 years to loop around the supermassive black hole. For comparison, Jupiter takes about 12 years just to go around our sun.
Right, and Sagittarius A star is about 4 million times the mass of our sun, so the physics environment S301 is living in is nothing like anything in our solar system. This was found by a team led by K. Abdel Dayem at the Paris Observatory, working with Felix Mang and Stefan Gillison at the Max Planck Institute, Juan Osorno at Paris PSL, and the broader collaboration is directed by Reinhard Genzel, Nobel laureate for his work proving Sagittarius A star is a supermassive black hole in the first place.
So why does one extreme star matter beyond just being a cool record breaker?
Because an orbit this tight and this precise becomes a physics instrument. General relativity predicts that a spinning massive object drags spacetime around with it. It's called the lens-Thirring effect, or frame dragging. We've measured tiny versions of this effect around Earth with satellites. Nobody has ever directly measured it around a supermassive black hole, because you need a star orbiting close enough, fast enough, and predictably enough to detect the tiny relativistic wobble it causes.
And S301 threads that needle.
That's the hope. The team thinks that with continued observation, they could measure Sagittarius A star's actual spin within a decade. That would be the first direct spin measurement of any supermassive black hole anywhere. Not modeled, not inferred from surrounding gas, measured from watching a star get pushed around by the black hole, literally dragging space itself.
A decade's a long wait, but that's a hell of a payoff.
Worth the patience. All right, moving on to our last story before we get to tonight's sky. And this one's a quiet result that could have a pretty loud effect on cosmology.
How loud are we talking?
Up to 4 times loud. A team led by Chloe Chang at Leiden University looked at 9 quiescent galaxies, meaning galaxies that have basically stopped forming new stars, sitting at a redshift of about 0.7. They used James Webb's NIR SPECT instrument combined with data from the Very Large Telescope's LEGA survey to look really closely at the actual population of stars inside these galaxies.
And found something we'd been missing.
A lot of something. Turns out these galaxies contain far more faint, low-mass stars than anyone had accounted for. They'd simply been outshone and hidden by the smaller number of bright stars in the same galaxies. Once you properly count the dim ones, the true stellar mass of these galaxies goes up by something like a factor of 4.
4 times the mass just hiding in plain sight?
Hiding in plain sight. And it wasn't random which galaxies had the most hidden mass either. The oldest galaxy in the sample, one that started forming stars less than 500 million years after the Big Bang, had the largest hidden population of low-mass stars.
Why would older galaxies hide more mass specifically?
That's the open question, and it's a genuinely important one because it means the ratio of small stars to big stars, what astronomers call the initial mass function, might not be the same constant everywhere and every when the way models have generally assumed. If early galaxies systematically formed proportionally more low-mass stars, every mass estimate we've made for the early universe using the standard assumption could be off.
Which affects a lot more than just these 9 galaxies.
Right. It touches how we calculate galaxy masses across basically all of early universe cosmology. And there's a nice side effect, too. More low-mass stars means more potential hosts for rocky, Earth-sized planets in the early universe. This was published in Nature Astronomy under the very on-the-nose title, Hidden Mass in Early Galaxies Revealed by Bottom-Heavy Initial Mass Functions.
The early universe just got a lot more crowded and a lot heavier in one paper.
Webb keeps doing that to cosmology this year.
All right, let's get people outside tonight. What are we looking at?
Grab a telescope if you've got one, because tonight's a genuinely good moon night. It's about 56% illuminated right now, and if you look right along the sunrise terminator, that line between lit and shadowed, you'll find the crater Theophilus down along Mare Nectaris.
What makes that one worth hunting down specifically?
With the sun that low on it, the shadows are dramatic. You get Theophilus's sharp, heavily terraced walls standing out in real relief. Plus, a big multi-pointed central peak casting its own shadow. It's one of those craters that actually looks 3-dimensional through a scope tonight, instead of just a flat circle.
And for anyone without a telescope handy,
Step outside right after sunset and look west. Venus is still an absolute beacon out there at magnitude -4.1, easily the brightest thing in the sky besides the moon. And if you're an early riser, Saturn's moon parade that we mentioned last episode is still running in the south-southeast before dawn. Titan, Rhea, Tethys, Dion, all still lined up thanks to those unusually narrow, nearly edge-on rings.
good night to actually use the equipment instead of letting it collect dust.
Always is. And that's it for today's episode. Series 5, Episode 172 in the books.
Quick recap. LandSpace makes history landing Zuk-3's booster, a mega-Earth that refuses to follow the rules, a star that might let us finally measure a black hole spin, and James Webb showing us the early universe was heavier than we thought all along.
If you enjoyed the show, the best thing you can do is tell a friend, leave us a rating wherever you listen, and follow us on the socials at Astro Daily Pod for updates between episodes. And of course, check out our website at astronomydaily.io for further details on all of these stories.
We'll be back tomorrow with more from across the universe. Until then,
Keep looking up. Clear skies, everyone.